Hi everyone, my name's Dan Crankshaw. I'm a senior grad student in the Berkeley RISE lab. And yeah, I'm going to be talking to you today about a prediction serving system called Clipper that we've been working on for a couple years. So Clipper is a joint effort, so I want to acknowledge everyone on the team. It's a really great core team, and it ranges from everyone from undergraduates, including people who have just finished their freshman year, all the way up through senior faculty. So it's really a big joint effort. So before I get into it, I want to sort of set some context. And in particular, we're at the Spark and AI Summit. There's lots of talks about different parts of AI, and even in this session, we're going to be hearing about lots of different parts of productionizing machine learning or AI. So to set some context, let's talk about the machine learning lifecycle and how sort of these different systems fit into different parts of that lifecycle. So to start with, we have model development, where we do data collection, data cleaning, featurization, and figure out sort of how to train the model. After that, we have a production training pipeline that we run at scale on live data to generate the models that are going to be serving live predictions. And then finally, we use those trained models to do inference and make predictions on live new queries. So when people talk about machine learning in production, they're frequently talking about both of these pieces, both the training and the inference at scale. So when we think about systems like Spark, Spark really excels at the training side of things, doing large-scale training on live data, scaling to large amounts of compute and data. But when we start to think about inference, and when we need to make predictions in tens of milliseconds under heavy load, we need to think about new systems that are designed specifically for these workloads and not just designed and not just modified batch training systems. So with that context, in this talk, I'm going to start with talking about the requirements for this new type of system, these prediction serving systems. Then I'm going to give an overview of Clipper and talk about how its architecture meets these requirements. I'll talk a little bit about the current status of the system. And then if there's time, I'll talk about some future directions. All right, so let's get into it. What are the requirements for a prediction serving system? Well, I want to make the claim that there's three core requirements for these systems. First, they have to be manageable, they have to be fast and scalable, and they have to be affordable. So what do these requirements really mean? Well, by manageable, the first thing that we have to do is we have to be able to get models into the system. A prediction serving system isn't very useful if we can't even get models into it to deploy them. And in particular, there's a wide range of machine learning applications and frameworks. And it should be simple to deploy all of these different models that are being developed. All the tools in this ecosystem have their place. And we don't want to tie the hands of data scientists and restrict them to a particular stack. Second, once we have the models in the system, we should be able to debug them and figure out what they're doing and why they're doing them. And then third, we need to be able to monitor both the system performance and the model performance. When we talk about putting machine learning models into production and serving them on live queries, we have to worry about all of the performance constraints of your traditional data serving systems, making sure that we're not using too much compute and memory and all of these things. But we also have to worry about model performance. Are the predictions that our models are making, are they accurate? All right, now let's talk about being fast and scalable. So this image is a picture of GoogleNet, which is a state-of-the-art-ish deep learning neural network from like 2015. Basically what we're seeing is that models are getting bigger and they're getting deeper, and yet we still need to make low and predictable latencies to serve these models for interactive applications. We need to be able to make predictions within the envelope of human cognition. And because these models are being put into increasingly important applications, we need to be able to scale to high throughputs as these applications scale and get new users and increase traffic. And to do all of this, we need to be able to serve our models on specialized hardware. And that's what brings us to this third point, affordable. We need to be able to minimize storage cost. We don't want to be storing a bunch of data or a bunch of predictions that aren't going to be used, because storage is expensive, but more importantly, we need to be able to minimize compute cost because these expensive resources, this specialized hardware, is really, really expensive. The latest generation, the Voltas from NVIDIA, the latest generation GPUs, are somewhere between $8,000 and $20,000 a GPU. If that can do a couple hundred predictions a second, and you have workloads of tens of thousands of predictions, you're facing massive costs. And if your predictions are costing more than they're making you, it's not worth it. So let's look at a couple of the ways that people do prediction serving today. So there's sort of two common approaches. The first is to pre-materialize predictions, and the second is to put a model in a container. And I want to convince you that both of these approaches are insufficient to meet these requirements that I've laid out. So what does it mean to pre-materialize predictions? Well, after you've trained a model, you take all of the possible queries you might need, and offline, you score them in the same training system, in the same batch system that you use to train the model. This generates a bunch of scores that we can then store in a traditional data management system, something like a key value store. We can do all of this with standard data engineering tools, off-the-shelf systems, many of which are open source. And now we've transformed our prediction serving problem into a data serving problem by serving pre-materialized predictions. So when we get a query from an application, we just look up the appropriate prediction and return it. We're not actually computing the predictions on the fly. So this has the advantage of once we've rendered the predictions, we can do low latency serving, but it has some problems as well. Namely, it requires the full set of queries ahead of time. So this has been a traditional approach for things like content recommendation going back 20 or 30 years. But this means that our prediction serving tasks are limited to tasks with small and bounded input domains. They require substantial computation and space, so they already start to fail on our affordability requirement. Because you have to score all of the content for all of the customers. You have to generate all of the predictions that you might need ahead of time rather than lazily evaluating only the ones that you need reactively. And finally, they're also costly to update. If you get a new query, if your input set grows, you have to rescore everything. You can't just update that single prediction. So people have recognized these problems, and they've started to adopt a more forward-thinking architecture, what I call model in a container. I wanted to call it model in a box, but that's not very descriptive. So what does this look like? Here, after we train the model, we take that model and we stick it in a Docker container. But just a Spark model in a Docker container doesn't have any way to get predictions into that container. So then generally what people do is use something like Flask, if they're using something like PySpark or any of these other Python-oriented machine learning frameworks, and stick a REST API in the container. Then, when we have a query, we send that query to the container, we can scale out that container, and we get a decision back in real time. And so the advantage of this are that this is general purpose. So we're starting to tackle some of this manageability requirement, and it renders predictions at serving time. So maybe it's more efficient than pre-computing all possible predictions. Certainly doesn't have the same restrictions of working only on a small and bounded input domain. But it has its own set of problems. It requires data scientists to write performance-sensitive serving code, and it results in an inefficient use of compute resources because we're using throughput-optimized frameworks to render individual predictions. And finally, it doesn't have any support for monitoring or debugging models. So I hope that I've convinced you that these two common approaches to prediction serving, while they're starting to tackle these requirements, are insufficient for our needs. So now, can we design a system that does meet those requirements? And that's where Clipper comes in. So now I'm going to give a little overview of the Clipper architecture and then talk about how we meet each of these three requirements. So from its inception, Clipper's driving design goal was to be able to serve this wide range of applications and frameworks, be a general purpose system that still can meet these performance and affordability requirements. So how do we do that? Well, we inject a middle layer for prediction serving in between your applications and your models. This provides a common abstraction to help with manageability, and it provides a place to put system optimizations to make prediction serving fast, scalable, and affordable. When we look at the Clipper architecture, from a 10,000-foot view, it looks roughly like this. If we zoom out even more and look at what an actual Clipper deployment looks like, from the application's perspective, your front-end application that only wants predictions but doesn't really care how they're generated, all that it has to know about is querying the Clipper query processor. It doesn't have to know about anything else. And this is just a REST API. The data scientists put their models in containers, but these containers differ a little bit from the model in a container approach that I described earlier, and we'll get to that in a second. Then, of course, we have a way to configure and manage the whole cluster, the whole system, and a little client-side Python library to make that easy to do. And then finally, we introduce Prometheus to monitor the entire system to make the system and the prediction serving applications more debuggable and provide more visibility into what's actually going on. We're designed to run on Kubernetes in a microservice architecture alongside your other applications. Sorry. And the actual, when we think about the actual system, it's actually pretty lean. It's kind of nice. It's about 10,000 lines of C++, and then about 8,000 lines of Python to configure and manage everything. We're open source under the Apache license, and we're designed to support production-level query traffic by delivering low and predictable latencies that are scalable, affordable, and manageable. So how do we meet these prediction serving requirements? I'm going to start with manageable. There's two things that we do. We try and really simplify model deployment, and we allow you to expose and export custom model metrics through this by using common abstractions that require minimal effort from a data scientist. So how do you actually get a model into Clipper? What do these Clipper model containers look like, and why are they different from the standard model in a container approach? Well, just like the standard model in a container approach, we want to evaluate models using the original code and systems to make it easy to get your models from the training framework into a serving system. But what we want to do here is abstract away the performance-sensitive serving code from data scientists. We don't want them having to write performance-sensitive systems code. That's not their purview. Many data scientists don't even have a background in software engineering. It's not where their skill set is, and it's not what they're rewarded for. And then finally, we want to run models in separate processes as Docker containers to provide resource isolation because, as I mentioned, data scientists sometimes write buggy code. That's okay, but we don't want one model failing to bring down our entire cluster. So how does this container-based model deployment work? Well, from a data scientist perspective, all that they have to do is implement this simple model API. It has two methods. There's an init method to load the model into the container, and there's a predict batch method to render predictions. I'll talk about why it's predict batch in a second. Because this is such a simple API, we can support it in lots of different programming languages and provide cross-language compatibility within one serving system. So we have support for Python, Java, C and C++, and R. Then you take this model container implementation and package it along with any other dependencies that you have in a Docker container. But instead of putting a REST API directly in that Docker container and have your applications query it directly, instead we put a lightweight RPC client in it that knows how to talk to Clipper, to this middle layer. Because the applications are abstracted away from the models, we can have many models connected to Clipper all at once and have a single endpoint for serving predictions for all of these different models. And this common interface means that it's easy for Clipper to support lots of different machine learning frameworks and it's easy for data scientists to implement this interface and deploy their models into Clipper. But once you have, so that's pretty good. But there's a lot of data scientists who haven't even heard of Docker, don't really know what that's all about. So we asked ourselves, could we make this even easier? So one thing that we do is provide this library of model deployers to automatically and intelligently save all the prediction code and abstract away even the container building process from data scientists. The idea here is to capture both framework-specific models as well as arbitrary wrapping code, pre-processing logic, featurization logic, post-processing logic, capture all of that into the container, and replicate the training environment and load the prediction code into a Clipper model container automatically. So what does this look like? Well, if you have some model that you've trained and it's in a Spark cluster, what you want to do is be able to take that Spark model and directly deploy it into Clipper without having to go through these steps of manually building a Docker container. So what these deployers do is they take this model, they serialize it along with any code that you want to run when you're calling this model, automatically build a container for you, and then deploy it into a running Clipper cluster, all with one line of Python. We have a growing library of model deployers. So in Python, we currently support scikit-learn, PySpark, TensorFlow, PyTorch, MXNet, XGBoost, and any other framework that can be pickled, as well as support for arbitrary R functions. So this is how we make it easy to get models into Clipper. Now I want to briefly touch on a feature that we added recently to make it easier to debug models once they're running. So one of the things that we hear over and over again is that monitoring models is really important, but how you monitor them tends to be application specific. Well, we already have Prometheus as this monitoring infrastructure to deploy models, to monitor the system. So what we've added is a simple common abstraction that you can use across all of your different models to export common or custom model metrics into Prometheus, and then let Clipper aggregate them into Prometheus, serve them, and combine them with the rest of your system metrics. So all you have to do is import this metric package from Clipper, register a metric, and then report the value directly in your model container implementation, and then Clipper takes care of the rest. These are available both with our model deployers and custom containers, and everything's exported to Prometheus and taken care of for you. This lets users, in particular data scientists, track both physical performance and statistical performance of the model in just a few lines of Python, and lets them diagnose problems like model degradation, as well as find performance issues. So now let's talk about how we make things fast and scalable. So there's a couple things here. I come from a systems research background, so we have a bunch of systems optimizations to make that middle layer and this RPC system really, really fast and performant. And then we also have the ability to do fine-grained hierarchical scale-out on Kubernetes. And this is where having this middle layer really shines. So I'm not going to get into too much detail here, but this model abstraction layer provides places to implement high-performance, low-latency serving code, both on the RPC side and the REST side. It lets us do things like caching to automatically maintain per-function caches and do memoization, which is really helpful for certain classes of prediction surveying problems. It provides a place to implement these common abstractions, and it provides a place to do batching, which I'll talk about in a second. In terms of scale out and making things scale, there's sort of two needs here. So the first is that sometimes models are slow, and you need to replicate them to meet your throughput demands. But here, because these models are expensive, if this model is running on a GPU, you don't want to replicate it unnecessarily. Because Clipper adopts this two-tiered system, or this middle layer architecture, you can just replicate the individual models that are the bottleneck without having to replicate everything. In particular, without having to replicate this high-performance serving piece. But of course, sometimes you have workloads that are tens of thousands or millions of queries per second, and you need to replicate the whole thing. So in order to scale to really massive workloads and be fault tolerant, you can also replicate the entire cluster and scale out everything. And by integrating with Kubernetes and using Kubernetes deployments and services, that makes this really simple to do. So hierarchical scale-out enables fine-grained replication to minimize cost while scaling to massive workloads. And this is sort of giving you a flavor of some of the stuff that we do in Clipper, where making things affordable and fast and scalable are both at odds with each other and tightly intertwined. So now let's talk about making things affordable, making prediction serving affordable. So the hierarchical scale-out is one thing that makes things affordable. But we also do adopt a technique called latency-aware batching to maximize our resource utilization. So the problem here is that compute resources for prediction serving tend to be a huge cost sink. Many machine learning models require expensive compute resources to meet these interactive latencies, things like multi-core servers, GPUs, or other hardware accelerators. And models have to be initialized and warmed to respond to queries in tens of milliseconds. We can't wait till a query comes in to load a model and start using these compute resources. So these compute resources tend to be tied up at all times, which is expensive. So we want to maximize our resource utilization of tied up resources to reduce cost. So this is what we do. This is how we use batching. So batching helps for a few reasons. One is that we often get queries, the query serving workloads are often bursty. And so a single page load might generate multiple queries, which means that we can populate a batch. But more importantly, what we're serving is models trained in throughput-optimized frameworks that often can take good advantage of parallel hardware resources. But the problem here is that the optimal batch size depends on the hardware configuration, the model, and the framework that we're using, and the system load. So we adopt a latency-aware batching technique to maximize resource utilization without exceeding these tight latency deadlines. And in particular, we adopted an explore-exploit strategy where we adaptively trade off latency and throughput, where we explore increasing the batch size until the latency objective is exceeded, while simultaneously exploiting previous latency measurements from previous prediction batches that we've performed to estimate the optimal batch size for a given deadline or a given SLO. I'm running low on time, so I'm going to skip through this kind of quickly. But the big takeaway here is that both throughput and latency increase as a function of batch size. And so this adaptive batching technique lets us find the optimal batch size for a given deadline. And these batching results hold not just for neural networks, but also for classical machine learning models as well. So this is how Clipper adopts this middle layer architecture, this multi-tiered architecture for prediction serving that lets us provide a set of common abstractions to make Clipper manageable and usable from the perspective of both data scientists, front-end developers, and DevOps engineers who all have different responsibilities in a prediction serving system, as well as a place to implement system optimizations to make Clipper fast, scalable, and affordable. So let me give you a little bit of an update on the current project status and how you can use Clipper. So we just released 0.3 of the software. Some of the highlights I have mentioned in this talk. These include things like this metrics and monitoring infrastructure with Prometheus and the ability to export user-defined metrics, support for hierarchical replication and removing any single points of failure from the system, as well as several new model deployers to make it easy to get common machine learning models and frameworks into Clipper. From an adoption standpoint, we have several active collaborations, including with companies like SAP, Scotiabank, ARM, IBM, and AI Singapore. We have some initial users who are using Clipper in production, and we're planning on growing that number this summer. Most of these active collaborations have deadlines by the end of the year to get Clipper into production. So far, we have 29 contributors, and we're also looking to grow that number as well. And one of the things, in line with this management theme, is making it really easy to get started with Clipper. So we're tightly integrated with Docker and Kubernetes. We have Docker images available on Docker Hub. You can install this client-side library with pip, and that's all you need to do to get Clipper started. You don't have to compile anything, clone anything, provision any machines. You just need Docker or Kubernetes and Python. So I'm kind of low on time, but briefly, we have a few future directions that we're really excited about, and I'm happy to talk to you about these in more detail after my talk. One is support for model selection and incorporating the ability to do things like multi-arm bandits, contextualization, personalization into this serving system. A little bit more research-oriented is support for model composition and more complex machine learning applications that are composing multiple machine learning models in arbitrary DAGs to render single predictions. And then the third is support for integration with this emerging class of workflow systems, things like MLflow, which was announced yesterday or today, as well as things like Kubeflow and SageMaker. So I'm going to skip through my details here and wrap up. So to wrap up, Clipper makes prediction serving manageable, fast and scalable, and affordable, which existing approaches of pre-materialization or naively putting a model container in a box with a REST API are insufficient to do. Check out the 0.3 release, which you can install with pip. Check out our repo. Check out our website. And we'll welcome new users, new contributors. And now I'm happy to take any questions. Thank you.
So about the model metrics, I see how you can get latency information there, but how do you get model performance information when the performance of the model is external to the serving system?
That's a really good question. So the question was, how do we use these custom model metrics to actually measure model performance? What could you actually measure? So there's two classes to measuring model performance, or there's two ways of doing it. The first you can do without any feedback. So this is things like measuring model skew, distributional shifts, things like that, which you can do directly with the queries that you're receiving and the predictions that the model is producing. So if you notice that suddenly your binary classification model is always predicting 0, that might indicate a problem. For more sophisticated measures where you need feedback and you want to figure out whether your model is actually making accurate predictions, right now this is insufficient. We're going to be doing some work this summer to try and identify more sophisticated measures for doing this type of monitoring. But this is very much an open problem, both within the Clipper project as well as sort of in the industry in general. I think your mic is cut off.
Thanks for the talk. It was a nice talk. Can you share some of the benchmarks regarding, for example, under similar workloads and similar kind of models? For example, you have let's say 5 Docker containers, and then you deploy 5 model containers, and what was the latency improvements that you saw and something like that?
I don't have any slides on that. I'm happy to talk to you about that offline. But in general, we can serve predictions on the order of tens of milliseconds. One of the things I didn't really mention, but we have basically when you deploy applications, you specify a latency deadline for predictions that you want. This helps us do adaptive batching. And those latencies work well with deadlines as low as 10 milliseconds. Can you speak up a little bit? So the question was, how do we compare to things like TensorFlow Serving or TensorRT? So the answer to those two technologies is different. We're sort of similar to TensorFlow Serving, although TensorFlow Serving is limited to TensorFlow models. So that's one big limitation. And in fact, several of our users have found us after initially trying TensorFlow Serving and finding that it was inadequate for the range of models that they needed to serve. In particular, people frequently need to serve scikit-learn models or R models. TensorFlow Serving also does some batching, and I think a system that makes a lot of sense if you're in the TensorFlow framework, but many prediction serving applications are not in that framework. And so TensorFlow Serving is insufficient. I think it also leads some stuff to be desired on sort of the manageability side and ease of use side. TensorRT is a system for optimizing neural network inference on GPUs, and that's sort of complementary. So you could deploy a model that's optimized with TensorRT into a Clipper model container and get all of the performance advantages of TensorRT to speed up sort of model inference and the performance advantages of Clipper doing the sort of the rest of the serving code around that technology. So Clipper adopts a black box approach to deploying these models. That's what lets us be general purpose. And all of our system optimizations are oriented around treating models as black boxes. So that's outside of the scope of the project right now. I think there's very interesting complementary work on white box approaches to optimizing model performance that Clipper can sort of natively adopt. And one technology that we're very excited about that will enable some of that is optimizations driven through Onyx.
All right, let's thank Dan.
Thank you.